next up is Huacheng.
Thanks for the introduction. And today I'm going to talk about optimal lower bounds for distributed and streaming spanning forest computation. And this is a joint work with Jelani Nelson. Let's first do a warm-up and consider the following dynamic data structure problem or streaming problem depending on which community you belong to. So the problem is you're first given an initially empty graph G on n vertices, and I'm going to do updates to this graph. And in every update, I can insert an edge. I can insert this edge, insert that edge, and I will also make queries. When I make a query, the data structure you design, you must output a spanning forest of G of the current version of this graph. And the goal is to use minimum space. So the space will be the main parameter in the stock, and I'm not going to worry about how much time you take to handle these updates and queries. So if you think about this problem, its space complexity is quite easy to understand, which is n log n bits. For the upper bound, you could just maintain a list of edges in the spanning forest, and every time I insert an edge, if two endpoints are already connected, then you throw it away. Otherwise, you add it to the list, and the list can contain at most n-1 edges, and each edge needs log n bits to describe, and the upper bound uses all of n log n bits. And for the lower bound, when the final graph, when I make the query itself is a tree, then I have to basically output the entire graph. And by Clay's formula, there are n to the n-2 trees on n vertices. So in order to distinguish every pair, I basically have to spend n log n bits. This is the lower bound. So the space complexity of this problem when there are only insertions is out of n log n bits up to a constant factor. So what happens if we allow edge deletions? So in this problem, I'm only inserting edges. So what happens, I can also delete edges during each update. So the solution we had before doesn't work when there are deletions, because when an edge that is not useful when it's insertion, when in the insertion model, we can just throw it away. But when there are deletions, it might be useful later at the query time. So in extreme case where, for example, we could insert maybe all possible edges, then start deleting edges until I have only n polylog n edges left, and then ask what is spanning forest. Then if you do the calculation, even if I sample, for example, n to the 1.9 edges at the beginning, that's still not sufficient enough to guarantee a high probability of having a spanning forest stored in the memory at the end. So this problem seems much harder, but it turns out that there is a very space-efficient solution if we allow randomization and a small error probability. So Guha and Andrew McGregor designed an elegant solution to this problem that uses out of n log n cubed bits of space, and with error probability 1 over poly n. So comparing this solution to the incremental spanning forest problem, this is using only 2 more log factors. And the exact same algorithm with a different setting of parameters actually gives you a smooth trade-off between the space usage and the error probability delta. So then when the error probability is delta, then this algorithm uses n times log of n over delta times log n squared bits of space. So one natural question here to ask is, why are we using 2 more log factors? Is it necessary? Can we improve the bound? For example, if you look at this space bound here, so for error probability, for constant error probability, and for error probability being 1 over poly log n, in these 2 cases, you get the same bound. In both cases, you get n times log n cubed bits. But maybe this sounds a little bit strange. When I'm lowering the error probability, I'm not actually using more space. Maybe it is possible to save one of the log factors if I only require, say, 0.1 error probability. But it turns out that this is not possible. And the first main result of this paper is a tight lower bound for fully dynamic spanning forest in this case, for almost the full range of error parameter of interest. So we show that any data structure for fully dynamic spanning forest with error probability delta must use n times log of n over delta times log n squared bits of memory for any delta between 0.99 and 2 to the minus n to the 0.99. So the first observation is that we cannot hope to prove this exact bound for all possible delta. Because, for example, there exists an n² bit solution, namely just remembering the entire adjacency matrix of the graph, which achieves error property 0. So in particular, when this delta is smaller than 2 to the minus n, we cannot hope to prove a lower bound of this form. But we prove this lower bound, we prove this algorithm is actually tight all the way up to almost this limit. And in particular, when the error parameter and the error probability delta is a constant, it implies that we do need n times log n cubed bits of space. And we do need exactly 2 more log factors comparing to the incremental version. Questions?
Just to understand the comment about error probability 2 to the minus n, are you claiming that lower bound is n² at that time?
I think so. And then this paper, I mean, this theorem doesn't say anything about that regime, but I think n² is a lower bound.
So can the upper bound, so the upper bound only handles like the error 1 over poly n, right? But
yeah.
So is there any hope to push it to like smaller maybe? I'm not sure.
There's actually a smooth trade-off between the error parameter and the space. So for error probability delta, you get n times log n over delta times log n² bits of memory. So there's a smooth trade-off between from constant to 2 to the minus n.
So the upper bound can handle the regime when error probability is like 2 to the power minus n to some constant power?
Yeah.
Or
Yes.
it can handle that?
Yes.
Oh, okay, I see.
Just the upper bound would be useless. Because if delta is 2 to the n something, you get almost, I mean, you get n² approximately.
Yeah, depends on what this something is smaller than 1 or larger
exactly.
than 1.
Depends on something.
Yeah, for smaller than 1, it's still useful.
Yeah,
larger than
smaller
1.
than 1.
Yeah. Right. And it turns out that this same solution, the AGM sketch, also solves the following n-player communication game in the simultaneous communication model, or sometimes also referred to as the distributed sketching model. So what is this communication game? So this communication game has n players with their shared randomness, with shared random bits, and the input is a fixed graph on n vertices. Okay, now there are no insertions, deletions, so we just have one fixed graph on n vertices. And this input graph is distributed to n players such that each player only sees the name of one vertex and the names of its neighborhood. Okay, then depending on based on what they see, they are going to send one message to a special player called the referee. Then the referee must output a spanning forest with a high probability based on all these messages. And of course, in the communication model, the goal is to minimize communication. So in some sense, this setting is trying to compute a global function of the huge input, giving small sketches of local information, which could be useful in some distributed setting, where the whole input is too large to fit in one machine. Then we distribute it into different machines such that each machine computes a small sketch of this local information of this input graph, and then you compute the global function, evaluate the global function value based on all these small sketches. So the same solution, the AGM sketch, also gives an efficient communication protocol for this simultaneous communication game. So using worst case log of n over delta times log n² bits of communication per player with error probability delta for any delta greater than 0.
Sorry, another quick question.
Yeah.
The consistency is guaranteed, right? That's the promise, right? What the players see will correspond to a consistent.
Yes, it will correspond to some consistent graph, and they all see the same shared randomness. And also the referee also sees this random bits. And for this simultaneous communication game, there's also a trivial log n lower bound, because the referee has to output spanning forest, who needs to learn n log n bits of information. So on average, each player has to send log n bits. And again, for constant error probability, this is using exactly 2 more log factors. And the second main result of this paper is this algorithm is again tight in this setting. We show that any simultaneous communication protocol for spanning forest computation with error probability 0.99 must use log n cubed bits of communication on average. So an average player in expectation has to send this many bits if error probability is a constant bounded away from 1. So this is we show that exactly 2 more log factors are needed than the trivial information theoretical lower bound. And it's an interesting open question is that it turns out that our technique doesn't give us a higher lower bound when the error probability is lower in this setting. Unlike the previous streaming setting, we get a full trade-off for all parameters of delta. So for even if delta is something like 2 to the minus square root of n, our technique still only gives log n cubed bits of lower bound. So an interesting question would be whether we can get higher lower bound of this.
So you're also interested in the regime where delta is closer to 1?
We don't know yet. So this lower bound only holds when error probability is bounded away from 1. So in these two settings, although this problem is in these two settings are solved by the same solution, but if you think about it, it turns out that the hardness or the most difficult part in these two settings actually coming from different places. So in the first streaming setting where we have insertions and deletions, the most difficult part is to handle these deletions because without them, the problem is easy. But the data structure is allowed to look at the whole memory after each update and during the query time. So there's no localness issue in this setting. And in the simultaneous communication problem, there are no insertions and deletions. And the main challenge is to handle trying to compose messages that only depend on a local structure of the graph. And because of these two differences, one can imagine that the hardness proof should should be quite different because we should explore different parts of the hardness. And in this talk, I will only focus on one of these proofs, the second one, the lower bound proof for simultaneous communication game in the rest of the talk. Okay, maybe before we go into the actual details of the proof, it makes sense to look at the how the upper bound works, maybe from a high level. So the most important part of the upper bound is probably a linear sketch that the Adrian paper designed a randomized linear sketch that maps a random linear sketch that maps a graph which can be viewed as an n squared dimensional vector into a much shorter vector of length n times log n squared, such that this is a linear mapping with polynomial bounded coefficients, which means in the output of this mapping, each coordinate has polynomial bounded integers, which means you can encode each coordinate using log n bits. So that to encode the output, it takes n times log n cubed bits. And moreover, this output can be viewed as a concatenation of n things, such that in the ith block, it has log n squared dimensions, and this ith chunk can be computed from some local information of the graph from the neighborhood of vertex I. And more importantly, by looking at the sketch, the whole sketch, it determines a spanning forest with high probability, with probability 1 minus 1 over poly n. And this probability is over the randomness of the random choice of the linear sketch, and for every instance. So in order to solve the streaming problem, we just store S of g, this linear sketch in memory, and for each update, because it's a linear sketch, we can just compute the sketch of this single edge and then add it to the graph, or maybe subtract it from it. And at the end of the stream, by looking at the whole sketch, it determines a spanning forest with a high probability. And as we argued before, it uses n times log n cubed bits of space. And for the communication problem, the ith player just based on his local information computes the ith chunk of the output and then sends it to the referee. Then the referee concatenates all these S sub I, G, and obtain the entire sketch, and then based on which he will be able to output a spanning forest with high probability. And this uses a log n cubed bits of communication per player.
So what was the condition of S of G again, that you can reconstruct?
Yeah, S of G can from S of G you can compute a spanning forest with high probability.
I'm confused about how it's getting used in the second application, because when there's an edge, right, two players are going to be, in some sense, doing the sketch with that edge in mind.
Yes.
Would it cancel out or something when these things are added?
Sometimes, in some step of this construction, you will need to cancel these edges in order to find something useful. But they will appear in both players' input, and they will appear in both sketches.
But one will be positive and one will be negative, so they will cancel out in the item.
When needed.
But who knows which is positive and which is negative?
This uses this, the public random bit scan. And also you can say the higher, every vertex has a name, and the name with higher vertex has a positive sign.
Then everything gets canceled.
Okay. So in the remainder of this talk, I'm going to give a high-level idea of how we prove this simultaneous communication lower bound for spanning forest. So again, just recall that an unvertex graph is given to each player, and each player sees one local structure of the graph and send one message to the referee, who has to output spanning forest. And our theorem proves that an average player must send log n cubed bits when the error probability is a constant. And for this talk, I'm going to do two simplifications. One is I'm going to prove that the worst player, there exists a player who must send log n cubed bits. And I'm going to assume that the protocol succeeds with high probability, with probability 1 over poly n. And in fact, these two simplifications can be gotten rid of fairly simple, but fairly easily. But I'm not going to get into this in this talk.
So C is much larger than 2?
Sure. In fact, any constant or 0.1 is fine. Is also fine. So the starting point of a lower bound proof is the communication problem universal relation. And in fact, it's a special case of this problem in one-way communication. So in this special case, we have two players, Alice and Bob. So Alice gets one set. Usually, it's you can think of it as a binary string. So Alice gets one set S, and Bob gets another set T, which is a proper subset of S. And in this one-way communication problem, Alice is going to look at her input and the shared random bits and send one message M to Bob. And Bob, based on everything he sees, must output an element in the difference with high probability. So the complexity, or the one-way communication complexity of universal relation subset in this stream is completely understood. So Kapralov et al. Proves a tight lower bound for this problem. And in particular, when delta is at least 2 to the minus n to the 0.99, the lower bound simplifies to log of 1 over delta times log n squared. So in particular, when the failure probability delta is 1 over poly n, the lower bound gives the optimal length being log n cubed. And this is where the log n cubed in our bound comes from. But maybe at this point, it might still not be clear why universal relation is related to spanning forest in simultaneous communication. But on the next slide, I'm going to present this connection, why it's related to universal relation, and then present the key idea of our reduction. Okay. So suppose that now you are one of the players in this simultaneous communication game. You would like to compute spanning forest. Then what you see is one vertex V in the graph, and also a bunch of other vertices who are your neighbors, U1 up to UK. And this is the picture you see. Then based on this picture, you send one message, M sub V, to the referee, and also the referee gets a bunch of other inputs, and based on all these inputs, the referee has to compute a spanning forest. Okay. Suppose after you have composed this message M sub V, I suddenly tell you that there's a subset of your neighbors, this purple subset, such that for all vertices in there, this vertex V is their only neighbor. Okay, so what does this mean? It means that the referee, in order to find the spanning forest, the only way for this purple set and V to connect to the rest of the graph is through an edge from V to some other vertex in your neighborhood. So if you view the set V as the neighbors of V as a set S, and view this purple set, the set of vertices that whose set V is the only neighbor, as a set T, then in order to find a spanning forest, you must, the referee must find some element in the difference in S minus T. Okay. So does it make sense? So why doesn't this already give us a log n cubed lower bound? This is because the referee finds a spanning forest based on all messages from all n players. So even if I send a message m sub v to the referee may still learn something about my neighborhood from other messages. For example, the message from vertex u1 may also reveal this edge v sub u1, and it's not necessarily coming from this message m sub v. So to circumvent this issue, we are going to consider the following hard instances. So the hard instance of our reduction will be a tripartite graph consisting of 3 parts. And the middle column will be the vertices we mainly consider correspond to the vertex u in the last picture. Okay, so the middle column will have n to the 1 minus epsilon vertices, and the right column will have much fewer vertices n to the epsilon. And the left column will have n vertices, which are divided into blocks of size n to the epsilon, such that each vertex in the middle has a corresponding block on the left. Okay, so the idea is that we are going to randomly permute the name of these vertices, such that if you are one of these vertex vi in the middle, when you see your neighborhood, you don't know which ones are on the left and which ones are on the right. Then for each vertex vi, we're going to use its neighborhood to encode some set S sub I. And then we are going to use its neighborhood on the left to encode some subset of Si Ti. And we construct a graph to guarantee that all the groups on the left, capital Vi, their only neighbor might, the corresponding vertex in the middle, little vi, could be their only neighbor. That means in order to connect to the rest of the graph, the spanning forest must find for every vi in the middle some edge connecting vi and to the right. And because we are encoding set Ti as the neighborhood on the left, then this corresponds to finding some element in the difference of Si and the Ti. So why are we constructing such a graph? So imagine that you are the referee, and suppose that you receive all the messages, but you don't see the messages from the right column. So you don't see this message from here, you only see messages from the left 2 columns. Then from the left column, what can you learn? So from left column, every vertex, you only learn 1 bit, either whether they are connected to the vertex in the middle. So from all these messages, the only thing you learn is the set Ti for every I. And for the messages from the middle column, everyone composes a message that depends only on the set Si without knowing what Ti is. So if the referee doesn't actually see any message from the right column, essentially he's trying to solve n to the 1 minus epsilon independent instance of a universal relation. So for every pair Si and Ti, there's one of such instances. But the point is, we set up this graph. The point is, there are so few vertices on the right, so all messages from the right column combined, the length is much smaller than the number of vertices in the middle column. So all these messages combined cannot reveal much information about a random vertex in the middle. So essentially, for a random instance in the middle, the referee is still trying to solve this universal relation problem. So our hard instance will be first randomly partition the vertices into different sets Vi and also Vr to randomly permute the names. And then for each vertex Vi in the middle, generate hard instance from universal relation instance. And then we connect each vertex Vi to Ti random vertices on the left, and then connect Si minus Ti random vertices on the right. And this completes the hard instance. So, questions? So in order to make a reduction, the idea is to embed a universal relation instance into one of these SI and TIs, and then try to construct the whole graph and then simulate the spanning forest protocol. So the goal of this embedding is to, first we want to generate a graph G that looks like a hard instance. So when ST pair is actually coming from the universal relation hard instance, I want my graph G to look like the hard instance from the previous slide. And also I want the spanning forest, which is the output of this protocol, to tell us an element in the difference, which will be the output of the universal relation problem. And I want to make this reduction, I want to do this reduction with low communication cost and preserves the success probability. But due to time constraint, I won't have time to go through all the details. But the point is, we are going to construct some graph such that giving an ST pair, the distribution of G is a hard instance, and for every, if we can find a spanning forest, then by finding one neighbor of Vi in the middle that is in the right, we will be able to find some element in the difference. And eventually, because of this, before we have an argument that on the right column has very few vertices. So in total, they reveal very little information about the neighborhood of the middle column. So even if we don't know the messages from the right, we can still estimate or learn what is one neighbor of the vertex Vi on the right with high probability. And the difference here will be, there will be an additive error of 1 over n to the point 1. So at the end, we will get a protocol with failure probability delta plus 1 over n to the point 1, and with the communication cost same as the communication cost in the simultaneous communication model. And by the lower bound from universal relation, we get log n cubed lower bound when the error probability is 1 over poly n. So because of this additive 1 over n to the point 1 term, we won't be able to get a higher lower bound. Even if the initial error probability is much smaller, it will always be absorbed into this term. So one open question is whether we can prove a higher lower bound for this in this model when the error probability is actually much smaller. Can we prove lower bound that matches the upper bound of log n over delta times log n squared? And also our lower bound proof uses heavily the fact that we're actually computing a spanning forest rather than maintaining maybe this connected components or maintain the 1 bit if the whole graph is connected. So it's an interesting question to study whether we can prove the same lower bound if the problem is just to maintain this 1 bit if the whole graph is connected or not. And for this problem, the best known upper bound is still the same log n cubed if error probability is constant. Thank you.
How does this issue of added error not come up in the streaming model?
Yeah, in the streaming model, there's we use a completely different argument. So the point there is that we basically prove that finding one neighbor for each vertex in the end of the stream is already hard. So that corresponds to solving an independent instance of universal relation or support finding. So each vertex, you can focus on this vertex. I can insert a neighbor or delete a neighbor. At the end, I want to find any neighbor of this vertex. So there will be n instance of this. So that's the main idea, but the argument is very different.
Just thank Huacheng again.